Thank you for attending today's webinar, Augment Your Expectations, Not Your Battery, How a Disruptive Technology is Changing the Way Utilities Deploy Storage. I'm Kelly Pickerel, editor of Solar Power World, and before we get started, I wanted to go over a few housekeeping items. You can view the slides for today's presentation in the resource window on your screen, and please submit any questions related to today's webinar in the Q&A window. If we do not get to your question, our presenters may reach out to you afterward. Finally, if you're watching this webinar on demand, you can still use all of these features, including sending questions to our presenters. So let's get started with today's webinar, Augment Your Expectations, Not Your Battery. Today, we will hear from representatives at Enervenue and Storalytics about grid-scale energy storage and alternatives to traditional lithium-ion technology. So now I will turn things over to Jamil with Storalytics.
Thanks, Kelly. Hello, everyone. My name is Jamil Hussain. I'm the Chief Technology Officer and co-founder at Storalytics. I'm actually filling in position of my colleague, Momen Yassin. He had some technical issue with his audio and we were not able to resolve that in time. So with no further ado, let's go ahead and get started with the discussion. So today, we're going to talk about the Storalytics web platform as well as the Enervenue technology. And we will share some of the case studies that we have done to see how the Enervenue technology performs against typical tier 1 lithium suppliers. So first part of the presentation is going to be about the Storalytics review and the typical process of modeling energy storage system and what are the key factors you need to take into account in the design process of energy storage projects and what really impacts your total cost of ownership. And then we'll have a chat presenting about the Enervenue technology. And the last part of the presentation, I'm going to go through some of the case studies that we have done and performance benchmarking between Enervenue and lithium technology. So with that, first we'll start with a little bit of introduction about myself and Storalytics. So like I said, my name is Jamil Hussain. I'm one of the co-founder and the Chief Technology Officer here at Storalytics. My background is in power system engineering, and I have almost a decade of experience working with utilities, universities, research organizations. So really where Storalytics started as a collaboration between National Lab and universities back in 2016. Both myself and my co-founder had a lot of experience with the solar industry, where we were doing a lot of designing and modeling of solar projects, and what we have been using PV system a lot in those design. But as we transition to energy storage design, we see that there is a gap in the market where you do not really have a common simulation platform or modeling platform that focuses on energy storage sizing, your overall plan design of that aspect. So typically, each supplier, each integrator have their own operating practice, but the assumptions, the modeling details, everything varies from models to models. So we saw that there was a real gap in the industry on a common simulation platform. And that's what was the primary motivation for us to start working on Storalytics, as we see that to be the PV system energy storage. So we launched our first version in Q3 of 2021, and then till date we have got over more than 140 plus users in more than 10 countries. Here in the picture you can see a template of or a screenshot of our software platform. I'm going to go into that a little bit more in the later slides. Okay, so let's get into the typical or the design process that we adopt in designing energy storage projects. So we see it as a two-pronged problem, right? So first stage, you have to understand your need. So let it be a non-wire alternative, if you're participating in a market environment, a total agreement, or can be ancillary services. So you really need to look at what are the driving factors of the need perspective, and then if you're trying to meet all this application, what your profile should be looking like. So that's kind of part of the first stage where you deduce the profile that your project needs to meet. And the second part is that, okay, now you have a project profile or a use case battery dispatch profile that you want your project to meet. And there are some certain design parameter like your project life, things like that. So the question then becomes, how do you determine the best technology for your particular project? And how do you choose, optimize your overall system design? So that's the second part of it. So you need to do an upfront study first to determine what are the application you'll be doing and what your use case needs to be. And then you need to do a detailed study for that specific application to determine which technology is best for your need. So in that vein, when you're talking about choosing the right technology and the OEM for your specific use case, right now, if you look into the current marketplace, there's not a lot of focus on a specific use case, right? So you typically get a requirement around 365 cycles per year. Now, whether that's like an 365 cycles, like a deep discharge, like an energy arbitrage, so 1 cycle per day, or it's more like ancillary or market services where you're not doing a full cycle, rather a lot of intermittent cycles you are doing. So all these has different impact on degradation and battery sizing. But right now, what the market is doing, they are using very generic assumptions on the use case and then trying to choose the best. Because the supply chain market is very constrained, the storage market is constrained, they're trying to pick the battery that they can get their hands on. So not really focusing on the use case itself. So in the process, you are leaving a lot of value on the table. So where the storage platform comes in, that it helps you to really find the best technology for your particular use case. It allows you to compare different technologies so you can really see for your particular use case which is the best technology. So for example, like if you have a microgrid kind of application where you need to store energy for a longer duration time, so battery technology with self-discharge might not be the best fit. With a high self-discharge might not be the best fit. But if you are having a very high cycle application, then you need a technology which has a better degradation performance. So things of that nature you need to consider and really the impact of that is different based on the use case profile. So that's why it's important to really have a simulation platform that helps you to find the right technology for your right use case. And eventually all this comes down from a project financial perspective is a total cost of ownership, right? So you need to look at what is the total cost over the whole project lifetime. So on the upfront cost, if you just look into CAPEX, some technology might be more cheaper or more cost effective upfront, but then those might have larger costs throughout the operation. So like augmentation multiple augmentation cycle might be needed. You might need to do replenishment. So that comes into the picture. As well as there are costs for maintaining the performance guarantees, right? So if you have to maintain a farm capacity for a certain period of time, you need to pay for that as part, or also might need to sign up for some long-term service agreement to pay for that. So that adds to your O&M cost. As well as if you have a technology with a higher round trip efficiency, that adds to your energy loss. So that will need to be accounted as part of your project financial as well. So it's important to look at not the upfront cost, but rather the whole cost of ownership. And then the question becomes, okay, that's understood. So we need to look at the total cost of ownership. So what are the factors that impact the total cost of ownership? So the way we see it is there are two main prongs, right? So you have the technology itself. So there are certain characteristics of your storage technology that impacts different aspects that eventually impacts your bottom line, which is the cost of ownership. And then there are certain characteristics of the use case that also impacts that. So if I go into the storage technology, you got to look at the cycle life, the calendar life of the battery that directly impacts, your initial overfill factor or how many augmentation cycle you will need. So that has an impact on your overall cost. Then you have your round trip efficiency, your self-discharge. So that impacts your overall energy loss. You have to have your operational constraints. So different technology has different operational constraints. Some technology, and that also applies to a system level, right? So if you really cycle a module or a rack, maybe you can do 0 to 100%, no issue. But if you look at a system level, you look at the interconnection between different racks, the voltage drops, the management of voltages, those becomes issue. So on a system level, you might not be able to hit 0 to 100%. So sometimes it's limited. So those kind of operational characteristics you got to take into account from technology perspective. Then you have the auxiliary load requirements. Like for lithium ion, we know that you need a very temperature control environment to maintain the right environment for the batteries to operate. But there are other non-lithium technology where you don't need any kind of active temperature management. But for those technology, you might see some power or energy derating as the temperature varies. So you got to understand those features as well. And then you come to the use case side. So what's the C rate? I mean, you have a max C rate, so maybe a 4-hour, 2-hour system you're looking at. But what if, you're not going to operate the system at like C by 4 or C by 2 the whole time, right? Your C rates are going to vary. So understanding the composition of your use case profile, like how many times you're doing energy arbitrage, how many times you're doing frequency regulation, that's going to have an impact on your C rate, and that directly impacts your degradation. You have your total throughput. That's something you got to look at. So right now, industry is pretty comfortable with 365 equivalent cycles, but that throughput amount can vary depending upon your need. You have the depth of discharge. So whether you're cycling from 100% to 0% all the cycles or between 40 to 60, that has an impact. And that can significantly impact your degradation. You have to look at your average state of charge, the resting period between cycles. So all these use case specific factors also have an impact on your overall bottom line. So these are some of the things we're going to look at in our comparison between EnerVenue and the lithium system. So we looked at all these aspects, and we're going to present some of our findings in the later part of the presentation. With that, now I'm going to pass it to Chad to give us an overview of the EnerVenue system.
Great, thank you, Jamil. And I'm very excited for your next part of the presentation where you actually dive into the results. So some exciting stuff there. Hi, everybody. Glad to be here. Chad Spring, lead the business development efforts here at EnerVenue. I joined EnerVenue back in March of 2021, so fairly early on in EnerVenue's life cycle. Prior to EnerVenue, I spent about 4 years at SMA. Many of you, I'm sure, know SMA, large global inverter manufacturer. Led a lot of strategic PV and storage customer relationships there. And then prior to SMA, spent many years in the fossil generation side of the energy industry with Toshiba America Energy Systems, Ethos Energy, and Siemens Energy as well. So today, I'm just going to dive into EnerVenue's business, EnerVenue scale up, our differentiators, and our battery technology, and how we can be thinking about batteries differently than the traditional kind of run-of-the-mill lithium systems that really kind of lead the industry deployments today. So a little bit of history. EnerVenue's chemistry is known as metal hydrogen or nickel hydrogen battery technology. And that chemistry is not new. So it's actually a decades old, about a 40-year-old chemistry that was originally deployed by NASA in outer space applications. The reason they really loved this chemistry is because of its durability, its flexibility, its ability to be really rugged and durable in harsh climates. The drawbacks, though, it was very expensive. So it had a lot of platinum in the anode of the battery, drove costs extremely high. So in order to help make that more commercializable, maybe I made that word up, but commercializable in 2017, Stanford University took a second look at this chemistry. Through testing of advanced alloys, removing the platinum, they saw better performance, better durability, lower degradation, all at a line of sight of being extremely cost competitive with LFP NMC technologies. So in 2020, EnerVenue was then spun out of Stanford with the mission of commercializing and scaling up nickel hydrogen chemistry for the stationary energy storage industry. We were very excited. Part of our scale up here, just recently, 2 months ago, we announced the opening, or I should say the groundbreaking of our gigafactory in Shelby County, Kentucky. That will come online in early 2024. So that is coming along rapidly. So, to kind of go back to 2020 when we were founded just about 3 years ago, within that 3 years, we're now we're pushing 300 employees, announcement of our gigafactory, as well as other really exciting, tremendous kind of tailwinds in the industry helping to really push us along. You'll also, I'm sure, if you follow LinkedIn or any of the media publications, we've been fortunate enough to have some really great press. So most recently from Forbes, an article you can see there. We've been covered by Forbes a handful of times over the last few years. Canary Media, I'm sure everybody's familiar with them. Some nice write-ups there, and also definitely a shout out to Solar Power World. Thank you for hosting this event. There's also some great press you can find there on their website as well. So let's really dive in here. So looking at some of the ways to compare and contrast our battery technology with today's incumbent, the lithium battery systems. So obviously, we're all familiar with some of the safety concerns with lithium batteries, with fire and explosion risk. EnerVenue's batteries exhibit no thermal runaway risk, which means no fire suppression systems are needed. So you can actually find our UL 9540A summary on our website, on our resources page. I definitely encourage you to check that out, as well as a lot of very useful additional documents on that webpage. So no fire suppression really equates to lower cost from an OPEX standpoint, less complexity, while still having a very, very safe battery system. From an OPEX standpoint, no augmentation over an entire life of a project is needed. And I'll dive a little bit more into why that is. The degradation mechanism that you see with lithium, dendrite formations, and so forth, does not exist in this chemistry and the chemical reaction within our energy storage vessels. C rates, so really flexible in the way it's operated, anywhere from a 2-hour all the way out to a 10 or 12-hour system, as well as being fully capable of little microcycles, right? So with a solar smoothing or even grid ancillary services, being able to accommodate those is really a way that we compare with lithium. So while we have a lot of differentiations, we can compare in the sense that we can directly replace lithium chemistry in the same use cases where lithium shines today. From a life cycle, so this taps into the durability aspect. So 30,000 charge and discharge cycles over 30 years, which equates to operating a system at 3 full charge and discharge cycles per day. Now, that may not be a common use case today, but as the industry evolves and matures, being able to really tap into new ways to use battery storage is part of the messaging that we're getting out about this technology. Now, even over 30,000 cycles, it's still only degrading 14% state of health. So a slight oversize at year 0, which you're doing with lithium anyway, a slight oversize here, and you ride that out for the entire 10 or 20 or 30 year life of your project. Excellent flexibility from a state of charge. So 100% all the way down to 0%, and anywhere in between, it's fine, it's happy. It does not damage the chemistry to be at that 100% or at that 0% SOC. Really wide operating temperature ranges without any compromise to safety. So -40 up to 50 C without the need for HVAC. And again, even at those extremes, there's no risk of any thermal runaways, any fires. We already covered the fire safety risk. So a really, really durable temperature range there. And from a material standpoint, no lithium, nothing toxic, very readily available, easily sourceable components, really available on any continent. So that plays nicely into our global scale-up strategy, which is in parallel to our US scale-up strategy, where we can be looking at facilities or factories to build our batteries in various regions of the world to directly serve those markets. And as I mentioned, it's a proven chemistry that's been around for 30, 40 years. So let's look at what's actually in the energy storage vessel and how this chemistry works. So if we start on the right-hand side, we see the new catalyst. That's really the focus of the 3 or 4 years of work at Stanford University, where the platinum was removed, new catalyst was applied. So we electroplate our anode sheets, our cathode sheets, separator between those. Those are stacked in multiple layers. Those are then inserted into our energy storage vessel, which you see there on the left. And that's about a 6-foot long tube, if you will. We then apply a water electrolyte solution. It's capped, welded shut, fully hermetically sealed, no pumps, no flow in and out of that at all. It's all hermetically sealed, self-contained. During that charging process, that water splits and you're left with hydrogen gas at a low pressure. During the battery discharging process, that gas recombines back into water. So think of it like a reversible fuel cell meets electrolysis type of reaction. Looking at, again, the use cases where we really shine within a grid scale application. So paired with renewables, right? With solar, with wind, AC coupled, DC coupled, being able to really maximize and improve the dispatchability of those assets is absolutely key. Standalone battery energy storage systems for grid services, for energy arbitrage, energy shifting, that's all, of course, a great use case. Then there's some really interesting use cases with residential due to the fire safety messaging. Also, T&D tied systems with grid services, frequency regulation, voltage regulation, all that type of stuff. And again, all with the messaging of being able to cycle multiple times per day. So where you've got your 365 cycles per year with lithium, and that's kind of what you see from the utility sector when it comes to RFPs, now thinking outside that box and really being able to maybe do some energy shifting, but then also play in some ancillary service markets. And actually, Jamil will focus on a use case with that exact model here towards the latter half of the presentation. Looking at ways we can deploy our energy storage vessels. So, think your traditional outdoor rated DC block that's very common in the industry, but also because of the simplicity of our technology and the no fire risk and the temperature durability, we're looking at a really differentiated way to deploy our batteries on racks within buildings. So, think Moss Landing, Gateway, those are two pretty high profile building battery storage projects, much, much simpler with our technology. So from a commercial risk standpoint, right? If we look at the existing lithium industry, the way warranties are written, very complex, very laborious to look through and really digest and manage an energy storage site within those guardrails. So enter Venue with that message of simplicity. We are really focused on being user-friendly, right? Being flexible in the way that the asset owner is operating our energy storage vessels. So our warranty is a 20-year, 20,000 cycle warranty, guaranteeing up to 88 or guaranteeing at least 88% capacity remaining in that 20-year or 20,000 cycle lifespan. So a totally differentiated, exciting way to be thinking about energy storage moving forward. And that's the end of my presentation. Thank you all. We do have a poll. Curious to hear the audience's feedback here. So if you recall, we spoke about augmentation and the need to not augment with Enter Venue's batteries. And we'll look at that again with Jamil's next portion of the presentation. But curious to poll the audience here. What do you perceive to be the greatest risk in augmenting an energy storage plant's batteries years after commissioning? So curious to hear what the crowd views as the greatest risk in augmentation. We'll give people some time. Let's give it another 10 seconds. All right, 3, 2, 1. Thanks, everybody. Okay. I would say this is a pretty one-sided poll here. So compatibility issues due to technology advancements made between commissioning and augmentation. Looks like that has the greatest concern from the polled audience. With second, the availability of components due to supply chain constraints, right? I'm sure over the last 3 years in a state of COVID, that certainly is a major concern with what we've seen. And then the third concern here is uncertain future financial incentives, right? That seems to be always in flux as well. So great. Thank you, everybody, for your feedback. I'll turn it over now back to Jamil to dive into some of the use cases.
Great. Thanks, Chad. All right. So yes. This slide here, now the next section here, we're going to focus on some of the use cases that we have done. So particularly, we have done 2 use cases to compare the performance of Enter Venue's nickel hydrogen system with lithium LFP providers. So we have first use case, which is the high cycle count. So like Chad was talking about, we are looking at multiple cycles here per day. And then we are adopting an overbuild strategy for both. So both Enter Venue and lithium is going to be an overbuild. So you're going to be overbuilding for the whole project life. And these are deep discharge cycles. Use case 2 is relatively less amount of cycling. So we have around 1.75 cycles. And then you have augmentation for lithium system, but Enter Venue is still overbuilt because you don't really need to do any augmentation for Enter Venue. Some of the things to note before we go into the results about the assumption of the study. So both the Enter Venue and the lithium models that we used are fully validated with OEM data. So we are using models that are built in the Storylytics platform, and these models have been validated with OEM data. Some of the characteristics of these models are the models captures capacity degradation accurately. It captures self-discharge, round-trip efficiency, and the temperature impact. Something to note that the balance of plant cost and the EPC or any kind of engineering cost is not included. So the numbers that we'll be showing is basically the cost of the DC block, your PCS, and then your energy cost, and then cost for maintaining your performance guarantees. For lithium augmentation, we have used the market data from August 2022 for some of the forecasted price that we have used in the augmentation of lithium prices. And then we are not considering the auxiliary loads as part of this study, specifically because the model that we developed for this one, for NRVN, was specifically at 20 C temperature. And that's because of the data that was available during the time of model creation. But then we didn't want to penalize the lithium system adversely, because we know if the temperature varies, there is going to be impact on the auxiliary consumption of the lithium system. So to make it an apple-to-apple comparison, we did take out the auxiliary loads. So all the results that you see here, along with the white paper, the simulation files, are located in this link here, download simulation files. So if you have a specific use case in mind that you wanna see what the outcome are gonna be, or compare both the technologies, you can actually go and download it. And you have to download the Storylytics software, and then you can run your specific use cases yourself. So with that background, this is just an example for you to show how this model looks like in the Storylytics platform and some part of the validation results. So we have like a separate file structure for the models, battery models, and then you have different tabs. You have general tabs, you have cell informations. Some of the numbers are not, it's basically striked out because you get that with the licensed version of Storylytics. But these are some of the parameters we have, and then we have degradation specific parameters as well, part of the model. Here you can see that a small portion of the validation on the model and the test data. So really showing that on the SOC range, our error percentage is between 1 and minus 1.5, so 1% error. And the power side as well, the differences between the test data and the model data is minimal, so which kind of gives us confidence on the model. And this similar approach is taken for all the lithium LFP models that has been used as well. So now getting into the case studies themselves. So like we talked about, so we are taking a 25 megawatt, 4-hour system. The project life is for 20 years. The requirement is that you got to maintain 100 megawatt hour throughout the project life. And the use case here is this one, right? So you have multiple cycles happening. So you have charge happening at the night time, in the morning hours, you are doing discharge, and then again, maybe during a high solar penetration, you are doing some solar charge and then discharging again. And then the later part of the day, you can participate in some of the market signal, like ancillary markets as well. In this case, this is a PJM example for the frequency signal for this portion. So the idea there is to, if you have multiple cycles happening, what is the impact is going to be and how these two technologies is going to compare. On the right-hand side, you can see our scorecard. So basically, in summary, what you can see is that the NRVN system is excelling in terms of degradation performance. So they have better install life capacity, as well as average degradation rate, and also the usable depth of discharge. So on a system level, you can achieve more. You can go from 0 to 100% compared to lithium system, which are limited on a system level. And then on the self-discharge and the cycle RTE, which is the round trip efficiency, the lithium system performs better than the NRVN system. So now the question is, okay, so we understand the technical differences. So what is the impact of this on the overall financial of the project? So that we address on the next slide after this one. So this slide is just a snapshot of you showing how we're modeling this in the Storylytics platform. There are several tabs here. I mean, you can choose the battery model, you can choose the inverter model, you can input the use case profile that you want to simulate, and then you choose the configuration of the system, and then you run your simulation. On the left was the Enervenus system. On the right is the lithium system. So with that, so now comes some of the driving factors behind the differences that we saw. So one of the thing was is the degradation performance. So like you can see, in this particular case, lithium system degradation was way more degradation per year was happening compared to the lithium, which showed very minimal degradation over the project life. So what's the outcome of that, right? So the outcome of that is for a 100 megawatt hour project, 2.1 cycles daily, we needed about 112 megawatt hour at beginning for Enervenus system at year 0. But for lithium, we needed around 219 or 220 megawatt hour. So that's kind of the scale in difference we're talking about. So if your installed capacity required is a lot more, that basically ends up impacting your overall project cost as well. So in this particular case, we looked at the overall CAPEX cost for the DC block. Enerven was around 39 million, and which was significantly less than what lithium would cost, is around 62 million. Other impact is that the Enervenus system did have a lower round trip efficiency, around 90% compared to 97% for the lithium. And this is, we're talking about DC to DCRT here. And for a C/4 case. So another aspect is to quantify this impact or this difference in round trip efficiency, which is captured in the energy loss. So as we know, battery system, they don't generate their own energy. They store energy, and in the process, there is some losses. So that losses needs to be accounted for the overall cost of the project. So we saw that for the Enervenu one, the cost was around 14.7, which was more than 3.43 million for lithium. But so in one aspect, Enervenu was more costly in terms of round trip efficiency and losses, but then in terms of degradation, it was much more cheaper. But overall, what we saw for this particular use case is that Enervenus one was the most cost-effective and the better option. So you can see the breakdown here, and I'm going to go a little bit more detail on this slide. So really, this slide gives the breakdown of the numbers. So, but something to note here, as you can see that for lithium system, the yellow one, which is the energy loss, was not as much impactful. It was a small portion of the overall cost. Most of the cost was done or incurred by the cost of the lithium batteries themselves. But for the Enervenus system, the overall DC block cost was less, but they have a significant portion of the cost was because of the energy loss and the low round trip, relatively low round trip efficiency. So on this one here, this just highlights some of the numbers. So as you can, we already talked about the DC block cost. You could see the difference, and then you can see the difference on the energy cost. So we could actually converted that into net present value, and you can see that the cost differential there. And overall, it brought us down to what we term the metrics that we like to use typically is the effective cost per required end of life energy. So in this case, the end of life required was 100 megawatt hour, and that needs to be maintained throughout the project life. So for that, we saw that Enervenus dollar per kWh effective cost was much less than lithium system. Okay, so that covers our first case study. So on the second case study, we wanted to do something a little bit different because we're seeing a lot of market discussion going on around augmentation for lithium system. So this is the project requirement is almost similar. We have 25 megawatt 4-hour project, 100 megawatt hour. The cycle count is a little less compared to the last case. And also for the lithium-ion system, we are using an augmentation approach. So the profile here itself is almost similar, but they don't have any ancillary or market participation. So you are charging at the beginning of the day, then discharging during the morning hours. During the day, when the solar is high, you are charging from the solar, and then discharging at the evening hour. So in this particular case as well, we saw a similar trend in the technical differences. So degradation was better. That led to better initial capacity and degradation rate. Losses and self-discharge was more, which led to more self-discharge. I mean, the self-discharge now score for NRVN to be lower than the lithium system. The numbers are different, but the generic trend that we saw for this particular case is similar as well. So in this one, we can look a little bit deep into the overall augmentation that happened for the lithium. For the NRVN, it was overbuilt. So the same overbuilt around 113 megawatt hour was needed for the whole 20 years. So that's like 10% overbuilt. For compared, in this particular case, we were doing 3 augmentation cycles. So we started with 127.5 megawatt hour. So around 25% overbuilt for lithium. Around year 5, we needed to add some more capacity to maintain more than 100 megawatt hour. So we did around 30 megawatt hour of augmentation at phase 2. Then around year 12, we did a replenishment cycle. Now that varies. Typically, anywhere between 12 to 20, you will do you want to do a replenishment cycle for the lithium system. So in this particular case, we are using at year 12, we did the replenishment. So replenishment basically means you take augmentation means you have your old cells, you go ahead and add some more cells in terms of capacity. But replenishment means that you basically replace your old cells as well. There are quite a few different strategies of doing augmentation. You know, you have your SC augmentation, you have your DC augmentation, you can have DC to DC converters. In this particular case, we are just assuming DC augmentation. There was no cost included for DC to DC converters. So just to make it clear, we didn't account for any DC to DC converter cost. So the things to note here is that the NRVN system did not require any augmentations compared to lithium needed multiple cycles of augmentation. We see impact of that on the overall cost. So the overall cost was around 39 million for NRVN, but then lithium, there was an initial CAPEX cost, but then there was an augmentation cost as well. So all this together was coming out to be more than what NRVN had. Similar, I would say conclusion on the round trip efficiency, like the first case. So we have almost similar results here. But of course, this one you see a little bit less round trip efficiency because we are not cycling as much here, like the previous case. So on this particular case as well, what we saw for this particular use case and the augmentation approach that we have taken on this use case, the numbers were working in favor of NRVN overall. So it meets your project requirements as well as overall it's more cost effective for this kind of application. Now you might have a little different sets of assumptions on your augmentation approach, your replenishment cycle. So I would suggest you all to download the project files and put in your assumptions so that you can see the cases that best suits your needs and your sets of requirements. Same here. The one thing I'm just going to focus is that, yes, the augmentation cost was around 30 million for lithium system, which was not there for NRVN. So you could see that reflected here, that there's a big portion of the overall DC block cost is going into the augmentation. But in terms of the generic conclusion, we saw the similar trend, like we see for the use case. So something we'd like to share with the project designers, the things that you need to consider as you are doing. There's a lot of traction going on in the energy storage industry, a lot of projects coming online, a lot of manufacturing being brought on in the US as well. So certain things, it's important for you to look into the modeling aspect and the sizing that basically can help you to optimize your project and help you design the winning project. So really, you got to do your use case specific data simulation if you want to get an edge over others. Generic market assumptions or degradation curves are good, but those are just good for very high level estimates. But for if you want to find the right technology and then you want to find the right overview factor augmentation, you need to do a specific detail simulation. You have to make sure your energy storage model that you're using are able to capture these following factors very like accurately, like capacity degradation. So there are several things that can impact your degradation. Now those varies from technology to technology. But for lithium, like your C rate, depth of discharge, temperature, those plays a very vital role. There are some other technologies which these factors might not be that impactful. But you need to have a very accurate model of degradation that can reflect all these different factors and their interplay. Self-discharge needs to be modeled correctly. You need to have your internal storage, like your RTE losses, and that varies over time, varies over your SOC range. You need to be able to capture that. Your auxiliary load assumptions. So you have your C, it varies with your C rates, your temperature, your container design, liquid cooling versus air cooling. So all these factors plays into your auxiliary load assumptions as well. So you need to have accurate, validated model for these to come up with good design assumption. Your inverter models needs to represent, temperature derating, DC voltage derating, compatibility with battery racks, right? So you need to, when you're doing the simulation, you need to put together a system that is actually viable. So you need to look into those as well. And most important of all this modeling that you're doing, comparing different technology, those needs to be happening in a common simulation platform for an apple-to-apple comparison. Otherwise, there are just so many differences, and those are difficult to capture. If you do not have validated model in a common platform. And other important factor is also you need to simulate your beginning of life and your end of life. So when you're designing a project, you need to make sure it's going to be able to meet the requirement at the beginning of the project as well as at year 20. So you need to do yearly, like all the year simulations to really get great confidence on your design. So with that, I think that will be all. So I think we can take some questions.
Hi, yes, thank you. We have now entered the Q&A portion of the webinar. So please remember you can submit questions in the Q&A box on your screen. We have a lot of really great questions come through. I'm going to ask some early ones, I think, that are more geared toward enter venue. So Chad, maybe you can answer some of these first ones. The first one is, if the enter venue vessels are pressurized, how do they not have more of a fire risk?
Good question. So a couple different facets there. Number one, it is a low pressure. So if we think of like a scuba tank, right, at 3,000 or 4,000 PSI, if we think at other hydrogen storage tanks are higher than that, fuel cells, are higher than that. We're at an order of magnitude less from all of those. So we're a few hundred PSI. So that really reduces that risk. The other aspect of that is, we're a unique battery chemistry, right? So not only do we need to be looking at standards for batteries, but also standards for pressure vessels. And so that falls into, there's hydrogen involved, so it falls into NFPA 855, for example. Our VP of product engineering is part of the 855 committee, right? So we have a lot of knowledge, a lot of expertise there in the way we're designing our batteries to make sure that there is no risk.
Okay, perfect. Yeah, this next question will be for you too, Chad. What are the main contributors to the lower DC-DC RTE of the enter venue system?
Yeah, good question. So Jamil actually hinted at it, that our energy storage vessels are just a tad over 90% DC to DC round trip efficient. So that compared with a lithium battery, just from a pure chemistry and chemical reaction standpoint, we're just not to that same 95 to 97% that you see with lithium, but also far better than what you see with some of the other non-lithium chemistries, which many times are in the kind of 60 to 70% range.
Okay. Yeah, maybe this one could be more for Jamil. Does the Storalytics software account for variance in self-discharge over the state of charge range? If so, what other factors are taken into account within the simulation?
Yeah, it does. Great question. So yeah, as we know, the self-discharge is a function of state of charge. So the higher the state of charge, the more the self-discharge is. As you go below as the state of charge goes down, the self-discharge rate decreases. But it also is a function of the temperature. So our platform takes both the state of charge and the temperature into account for the self-discharge model. Great question.
Okay. Next question is asking, what are the most impactful types of cycles for lithium? And does Storalytics software account for different cycle types?
Yeah. So for some of the characteristics of lithium is that if you have very high depth of discharge, so going from 0 to 100%, that kind of cycles has a much more effect on degradation that is detrimental to the degradation. You also have to look at your average resting state of charge. So where your state of charge is, typically the higher it is, the more impactful it is on degradation. So our platform takes those. So the way our platform works, it looks into the profile that you input, and it basically characterizes that profile based on these factors that impacts the degradation of the battery. So it characterizes your profile based on depth of discharge, your maximum C rate, your real-time C rate. Uh, it looks into your average state of charge. It looks into temperature. So all these factors are blended into the degradation model that we use.
Okay. Someone is wondering why the AC system cost is higher with lithium.
Yeah, so great question. So one of the limitations that we applied here is how much megawatt hour you can connect behind one inverter. In this particular case, we applied around 21 racks that you can maximum connect behind one of the inverters, and that's mainly because of the DC short circuit limitation on the inverter side, so that you cannot connect an infinite amount of energy behind one inverter. So once you apply that, and then you look at amount of megawatt hour you need to connect, that basically drive the number of inverters needed. So it's not basically driven more by the MVA rating, it's driven more by how much megawatt hour we need for lithium, and to connect them, we needed more number of inverters, and that causes the AC cost to be more.
Okay. This next question, I'm thinking it's maybe directed more toward the EnerVenue product specifically, but is it possible to extend the duration beyond 4 hours? Could it go to a 10 to 12 hour product?
Yeah, great question, and absolutely. So really a peak duration of 2 hours all the way out to 10 or 12 hours. So it offers that flexibility where you can adapt to maybe changing use cases, or even the use case within the first 5 years of a project may be different than the last 5 years of the project. And so that really allows you to have that flexibility to go all the way out into the long duration spectrum of 10 to 12 hours.
Okay, someone's wondering, does the EnerVenue system require voltage monitoring at the vessel level or only at the string level?
Yeah, so that's getting into our BMS. And so our BMS is custom in-house designed, and because it is a different technology, there are different things that we are measuring. And so voltage is one, pressure is another, and current. So really those three give an extremely accurate depiction of the state of charge of each energy storage vessel. So we do monitor that on each ESV or energy storage vessel, and not necessarily at the string level. So we want to see as much data and detail as we can.
Okay. Can the ESVs, can they be adapted and implemented worldwide?
Absolutely. So we have a really aggressive global scale-up strategy, and part of that includes really close collaboration with our strategic partners. So Europe, Middle East, Africa, Australia, India, China, all of those regions we are actively working in, and again, that's through our strategic partnerships. So the scale up in those regions is really kind of matching or pretty close to parallel with our scale up here in the US.
Okay, this next question, bear with me. It's a lot of acronyms and everything, but can you describe more the meaning of the cost of energy loss and the total running cost line items and the comparison of the ESV versus lithium?
Yeah, I think that's definitely a Jamil question. But maybe Jamil, before you answer that, a lot of these questions, right, that are really diving into the great work that Jamil and his team have done, you can find these white papers, the graphics that he shared in the detail. You can find those white papers on the EnerVenue website, on the resources page, and feel free to dive in and digest those. You can also find those through Storalytics resources as well. But sorry, go ahead, Jamil.
Yeah, thanks, Chad. I was gonna start with the same, but yeah, just quickly. So the total running cost has two components. One is to maintain the state of health guarantee, so maintaining 100 megawatt hour plus throughout the project life. Maintaining that guarantee has a cost. So part of the total running cost is that, and the other part is the energy loss cost. So basically, the energy loss cost basically means that you charge the system with a certain amount of energy, and then you discharge it. Of course, because of the losses, you do not get the same amount of energy out. So the difference between the charge energy and the discharge energy is accounted over the project life, and then that basically is the energy loss cost.
Okay, perfect. Yeah, so there's a lot of questions in here, and a lot of them are very specific. So I think we're going to wrap up the live questions right now, but please feel free to reach out to our presenters. And I know they're going to get a list of the questions after this webinar, so they will reach out to answer your questions more directly. But yeah, this webinar will be shared with all registrants, so you can view it again at your convenience if you want to go over some more of the data. So I would like to thank our speakers for being here and EnerVenue for sponsoring today's webinar. So thank you to everyone for joining us today, and hope to see you at more Solar Power World webinars in the future. Thank you.
Thank you, Kelly.
Thanks all.